All right. Got 5-1, day 2. We're shifting gears a little bit from, in the first day we kind of saw the identities and then used them to find trig values, and we're moving towards a topic that's going to be a little bit of a bigger deal in Chapter 5, to simplify trig expressions, okay? So you'll see these instructions pretty much over and over again in Section 1 and 2, that we have that trig expression and we want to simplify it, okay? Now, you'll see in Section 2 the instructions of verify. If you get the instruction of verify, it's telling you what you should simplify to. In a lot of ways that can be easier, because if you're going to simplify this expression, a lot of times what comes up is, when am I done? You know, when have I fully simplified? If you check your homework, you will notice I only assigned odds. So you have right in the back of the book, you could go and double check and see, oh, for this one, the back of the book says I need to simplify this till I get negative sine cubed. Okay, that's where I'm going. Okay? If we said that this equaled negative sine cubed, then it would be a verify. Okay, but you should treat all of them like that, and that's why they're all odds. Go look them up in the back and know what you need to simplify to. Okay? We left off in the first day doing some factoring. Okay? Anytime you can factor, you probably should. So on this one, I see two terms being subtracted. Both you can take out a factor of sine of x, which would leave cosine squared minus 1. Okay? Cosine squared minus 1. Sine of x. Now, I'm thinking of my identities. All right? And cosine squared reminds me of our Pythagorean identity that says sine squared plus cosine squared equals 1. Okay? Now, if I were to rearrange these terms, I could get, because this is something that you're allowed to do, you could take the identity and you can move stuff around. I could say sine squared plus cosine squared minus 1 is 0. And then if I were to subtract sine squared and bring that to the other side, I would have that. Okay? Now, you don't need to write all that out. I'm just doing it because we're new to this, and a lot of times if I don't and I make the substitution, a lot of you would be like, what did you just do? I could refer to the Pythagorean identity, but you would likely just think of that. Okay? The identities can be rearranged. Now, having done that, I see I have cosine squared minus 1. Okay, so this step is not going to affect sine of x, but I could replace that with negative sine squared. Okay, now every time I do use an identity, those for that step you should cite it. Okay, Pythagorean identity is a lot to write out, so if you just say pi, I know what you're talking about. That substitution that you made was justified by one of our Pythagorean identities. Multiplying these together, I get negative sine cubed, and done. Okay? Remember, we peeked in the back of the book and saw that's what we needed to get to. That expression has been fully simplified. Oh, look at this. New expression, same instruction. Okay? I'm starting in the same spot. You know, I got two terms being added. Can I factor? Okay? You can typically, you know, assume that if you can factor, you should. Now, I suppose, wait a minute, I'm getting ahead of myself here. Hypothetically, we should peek in the back of the book. If we did, we would see that the answer to this one is cosecant of x. We need to go step by step and show, with either substitutions with identities or just doing some algebra, that this trig expression can be simplified to cosecant of x. Okay? Now, the factoring setup kind of hits a dead end because I can't. Okay, I can't. There's two terms being added. They don't have anything in common. Sine of x, there's absolutely nothing I can do with my identities to substitute sine of x. Cotangent's a different story. Okay, there I can. We have one that states that cotangent is x's cosine value divided by its sine value. I'm going to justify that step with a little qi. That's a quotient identity that I used. Okay? You're going to find of all those identities you saw in the first day, Pythagorean, reciprocal, quotient. You're going to use those three a lot. Now I've got these two terms. If I multiply these, I have cosine squared of x over sine of x. Okay? I didn't use an identity, so I'm not going to justify anything. Now this step right here can be a little bit tricky. I've got these two terms. The second one is a fraction. I want to add them together, except sine of x isn't written as a fraction. I need to make it one. And if I make the denominator sine of x, the numerator would have to be sine squared. Okay? Stop for a moment on that step. Okay? Basically all I did is I multiplied sine of x over 1, and I multiplied the top and the bottom by sine. Because now I've got these two terms that have a common denominator, so I could write them as a single term and say sine squared plus cosine squared all over sine. Notice I haven't given any more justification at this point because, you know, I made that original substitution for cotangent, but I haven't used an identity since. Now I'm going to, right? And a lot of times when it's time to do a substitution with an identity, not all the time, but a lot of times it's obvious. The top of this fraction screams Pythagorean identity. Okay, you could substitute and put in 1. So for that step, I'd say I did a Pythagorean identity. And then we're almost there. The reciprocal of sine is cosecant, and that last step I actually do have to justify. If you use the fact that you can flip it to its reciprocal trig function, that's what the reciprocal identities state. And we do end up at cosecant. Whoops, we need to back up here. We'll do that one next. All right, now this is just a matter of irony. If we were to peek in the back on this one, we would also see that this one should also simplify to cosecant. Just a coincidence. Okay? We talked on the other two that if we could factor, we should. If we can find an obvious trig identity to substitute, we should. This doesn't have either one of those. Okay? What this has is two fractions that I would like to add together. Okay? I'd like to add them together. What's going to happen here for my denominator, because I've got some funky denominators, is anytime like you're just really not sure, you can take the two denominators you have and you can multiply them, which is what I'm doing. In very basic terms, I'm getting a common denominator. Now, if I go back to my first term, okay, I multiplied the bottom by sine of theta, which means the top was sine theta, which means it also needs to get multiplied by sine theta. Over here, we had cosine of theta. The bottom got multiplied by 1 plus cosine theta. So we need to do the same. Okay, we need to do the same. Okay. I'm writing out the bottom again, but the whole point of doing this was to combine them by adding them to get a single term. Okay, so now what I have on the top here, sine times sine, that's sine squared. That has potential. That, you know, anytime I see trig functions squared, I think of the Pythagorean identity, so I like that one. That looks good. And then over here, we'd have cosine times cosine. So we would have plus cosine squared. And then we actually have an extra cosine. Okay. Still no identities to cite because I haven't used one, though we're about to. Notice right here, sine squared plus cosine squared, that's 1. So the top will become 1 plus cosine over 1 plus cosine times sine. And of course there I'm going to have to say that was a Pythagorean identity. Next step should jump out at us. Those are going to cancel. We have 1 over sine theta. Didn't use an identity there. And we can get to cosecant theta using the reciprocal identity. So coincidentally, like the last one, we do end up at cosecant. All right, this one's a little different. If you get one like this, draw a picture, okay? Which I can do here. This problem is telling me that my angle, theta, is less than 90 degrees, so I can draw it in a triangle. And that's what I'm going to do. There's theta. So related to this triangle, there is something that is the square root of 4 plus x squared. Okay? And that is in terms of x, which is going to be a side length, right? Because here's what we know about our angle. X equals 2 tan theta. If I divide both sides by 2, I get this. That the tangent value of our angle is x over 2. Okay? Tangent is opposite over adjacent. That means this side on my diagram is x. This adjacent side is 2. And that would mean the hypotenuse would be 2 squared plus x squared. And then the hypotenuse would actually be the whole underneath the square root, and wouldn't you know, that expression that they gave us, okay, for this whole angle that it's describing, it's the hypotenuse, okay? So what we want to do now with a trig substitution here is it's basically saying write an expression, okay, for the hypotenuse, but x is a side length. Write it in terms of the angle, okay? Write it in terms of the angle. Now this part might require a little bit of guess and check at first, okay? I don't want x to be in my answer, okay? So I'm really focused on using this side and that side, which leads me to one of two possible trig functions, cosine or secant. Technically speaking, you could use either one. Secant's going to work easier. So if I were to set this up, I would say, all right, secant of theta is the hypotenuse, which is the square root of 4 plus x squared, over the adjacent, which is 2. And this works out really well, because if I multiply both sides by 2, the right side is just the hypotenuse, and I have my answer right here. Based on the information it gave me, there is an expression that would give me the hypotenuse from the angle. Okay, kind of an interesting way to look at constructing a triangle. You know, normally we think about we'd get the hypotenuse from other side lengths, which we could. That's what this expression right here would do. But if you just told me what the angle was, I could go secant of that times 2, and that would go directly to the length of the hypotenuse.